All right, so the last question here, we've got a stress strain graph. This is defined tensile strain, and it is the ratio of extension to original length. Again, you could write delta L divided by L if you define the terms. So you must define the terms, otherwise we have no idea what L represents. So breaking stress of copper, we have to look at the graph where the graph stops. Tensile stress. And it is somewhere between 1.8 and 1.9. But very, very, very close to 1.9. So I'm going to say that it's 1.89. But we have units, make sure to put times 10 to the 8 pascals, because it is not 1.89 pascals. 1.89 pascals is incredibly tiny, and that kind of thing would be crushed by the atmosphere. So, line where you consider plastic deformation may start, it needs to be somewhere in the curved area before the maximum stress, usually very near where the straight line part starts. So just somewhere in this area here. Okay, use the graph to calculate the Young's modulus. That is the gradient of the straight line portion. I'm going to mark it on here. We'll use a strain of 1 because we're dividing by strain, and that is about 1.15, I would say. 1.1. Yeah, 1.18, we'll say. Okay, so there's 1.18 times 10 to the 8 pascals, and divide that by 1.0 times 10 to the minus 3. And I end up at 1.18 times 10 to the 11, which equals 1.2 times 10 to the 11. And if I do it like that, it's pascals, and I can do 120 gigapascals then. And you have to put the unit for the final mark, because it does say state that. Okay, area under the line. Use the graph to find the work per unit done, or per unit volume, in stretching the wire to a strain of 3 times 10 to the minus 3. So, again, here we go. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Let's call that 33. That's 34. That's 35. That's 36. Say that, and that is 37. And so that's about 38. So approximately 38 full boxes. So 38 boxes times, and each box is 0.2 times 10 to the 8 times 0.5 times 10 to the minus 3, 5 times 10 to the minus 3, which equals 0.1 times 10 to the 5, which equals 1 times 10 to the 4, or 10,000. Okay, and that's per box, so times 10,000, which equals 380,000 joules per meter cubed. Okay, for here it says calculate the work done to stretch 0.15 kilograms of the sample to that. So what we need to do is figure out the volume. So density is volume, or is mass divided by volume. So volume is mass divided by density, and then my work done will be the area times that. So 0.015 divided by 8960 times 380,000. Times 0.015 divided by 8960. Which equals 0.64 joules to two significant figures. Okay, and the last thing, make sure I got that right. Yes, I do. And the last thing is, here we've got a certain material has a Young's modulus greater than copper and undergoes a brittle fracture at 176 millimeters. So draw a line showing this. So two key things: Young's modulus is greater, so it must be a steeper line. It's brittle, so it doesn't really need a curve. Okay, so I just need to go to about 1.76, so about here, just a straight line like that. And do I need to label it as something? Well, let's just call it 5F. Okay, so that should be it. It needs to be steeper, and it needs to show brittle strain at the right stress.